So, welcome back, and in continuation of my previous lecture, and now we are going to talk about the magnetic properties of materials. Materials have several kinds of magnetic properties. Okay, ferromagnetics, ferrimagnetics, paramagnetics, etc., etc. And there are, in fact, umpteen materials. Some of them are natural, some of them are fabricated, synthesized, this, that, and every material has like other properties associated with that, thermal properties, electrical properties, and many other properties. They have magnetic properties. So, in the first instance, before we discuss about the magnetic properties of materials, let us discuss magnetization and magnetic intensity. Okay, in the beginning. Now, in any material, we know that there are atoms, and the atoms, there are electrons which are circulating around the orbit, etc., and thereby they do have a magnetic moment. And for a given volume V, all these magnetic moments associated with all these revolving electrons can be summed up as m net, okay, for a volume. So if we have, for a given volume V, a net magnetic moment m net, then we define something called magnetization as m is equal to m net divided by V per unit volume. This has, m net has the unit ampere meter square divided by the unit of volume meter cube. It turns out to be ampere per meter. Okay. Now let us consider a long solenoid carrying current, okay? A long solenoid which is carrying current. So, this solenoid has got small n is equal to the number of turns per unit length, and it carries the current I. And we know that the magnetic field in the interior B naught is equal to mu naught n I. Okay. So this is an empty, or the one which you can say that the material inside is vacuum. Okay. Thereafter what we do is we fill this, the entire this volume over here with the material of non-zero magnetization. With the material of non-zero magnetization. So this field mu naught, it improves to a new value given by B is equal to B naught plus Bm, where Bm is the field contributed by the material's core. Okay. Normally, to increase this immensely, we have soft iron, etc., etc. So many kinds of force are possible. Okay. This field Bm is proportional to the magnetization. Okay, capital M, which is defined as m net upon V. This is proportional to this, and therefore we can say that this is equal to a constant mu naught times m. Okay, or where mu naught is the permeability of free space. So Bm is equal to mu naught upon m. Now, it is convenient to introduce another vector field H, which we call magnetic intensity. Okay, and it is defined as H is equal to field B upon mu naught minus m. So that field B becomes equal to mu naught H plus M. Naturally, both of them have the same unit, that is ampere per meter. Okay, like that. Here H is due to the external factors such as the current through the solenoid. Okay, and the second term M is due to the specific nature of the magnetic material. It changes from material to material. Now, what we have, we find that this M, this is also affected by H. Okay, the magnetic intensity, such that M is proportional to H, and this is equal to chi H. Okay, where this chi is the magnetic susceptibility and is naturally, because they have the same dimension, so chi is dimensionless. More about it follows. So we can write the magnetic field inside the solenoid, which has been filled with a magnetic material, and that turns out to be equal to mu naught into H, the magnetic intensity, plus the magnetization M. Okay, so I can write this as mu naught H plus M is equal to chi H. Okay, so chi H. I can take H outside, so this becomes equal to mu naught 1 plus chi H here. And you see that this 1 plus chi is written as mu r. Okay, where mu naught into mu r is equal to mu, and this mu r is the equal to 1 plus chi is relative permittivity, just like epsilon r is, relative permeability, just like epsilon r is relative permittivity in the case of electric fields. Okay, so mu naught into mu r is equal to mu naught 1 plus chi. Okay, and this mu is called the permeability of the material. Okay, mu naught is the permeability of free space. Okay, you understand that? Now there are a lot of lookup tables given in the books for the various materials, their value of chi, their value of mu r, etc. They are given, and you can look up in those tables for different materials of substance, materials that matter. Now we categorize the materials as diamagnetics, paramagnetics, and ferromagnetics. Okay, for diamagnetic materials, the value of chi is less than 0, that is, it is negative. So all those materials which have a negative value of chi, the magnetic susceptibility, which is of course a number only. Okay, so they are called diamagnetics. Okay, there is a kind of opposition that is present in diamagnetic materials. Okay. Paramagnetic materials are pro-magnetic field. Okay, and chi is more than 0, it is positive, H is small, the value is small. The ferromagnetic materials, which are categorized separately, they are also kind of paramagnetic materials, because they also have pro-magnetism, and the chi is again equal to greater than 0, it is positive, but it is having a large or a huge value. Okay, I wind up the lecture here for the day. And in the next lecture, we will have the details of diamagnetics, paramagnetics and ferromagnetics materials here. I can put S, these various materials that are there, and understand their properties, when and where to use them, and how they behave, and what is the mechanism by which the diamagnetics oppose magnetic field and paramagnetics improve the magnetic field which is present in the when these materials are not put inside the solenoid. Okay, so the presence of the materials as the core in solenoids or other things of substance which interest us, they all depend upon the materials that are there and their properties, and how these properties they arrive. We'll talk the details in the next lecture. So for now, I must tell you that I invite you to question, and I long to answer those questions, if I can, of course. So long, see you again.